These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So you tell me, this is one of the things that 3.2 has tests. Do you know how to solve this type of problem?
Okay. Well, here, can I try and do it on my screen?
Sounds good.
Okay. Where x plus 5. Well, that's not going to work. You can't factor that. Okay, so
Okay, let me give you some help now. Okay, so you had a good idea here. What you said is I don't know how to find this derivative, so I'm going to try to simplify it into something I can take the derivative of. And you had a good idea. If there was some way to factor the numerator and then cancel, that would be a good approach. The only way that would work is if there was an x minus 2 factor on the top, or a 3x minus 6. So I don't think that's going to work in this case. Most things don't factor nicely. All right, so sometimes that if the top factored and canceled with the bottom, that would work, but that's not going to help us in this case. So let me show you what the method is here. So the basic method that we're using here, well, let's take a step back and review some important techniques here. So, for example, let's say I have a function which is the sum of two other functions. There's a rule for finding derivatives. Do you know what this rule is? If f is the function of h and g, if you knew h prime and you knew g prime, do you know how you would find f prime?
you would add them together? And
That's what seems natural anyway, right?
right.
Since the function is the sum of h and g, it seems natural that the derivative should be the sum of h prime and g prime. Now, things that seem natural don't always work in mathematics, but this does. The derivative of a sum is the sum of the derivatives. When you're taking these derivatives, you just take the derivatives separately and add them up. This is the sum rule.
Okay.
And let's say you had this, then. Any idea, whoops, any idea how you would find, take a guess, what would f prime be here?
Would be h prime of x minus g prime of x?
That seems natural, and fortunately, it works that way. You might not realize it, but we've been using those rules all along. For example, your textbook tells you how to find this type of derivative, right? X to the fourth equals 4x cubed. Take the derivative down, take the exponent down and subtract by 1. But then how did we find, say, this type of derivative? Well, do you see, you were actually using the sum rule without explicitly thinking about it. Basically, you said, well, the derivative of x cubed is 3x squared. And the derivative of 3x squared is 6x. And the derivative of 7 is 0. And since f is this minus this plus this, f prime should be the derivative of this minus the derivative of this plus the derivative of this. So if you see what I'm saying, you were using the sum and difference rules already without thinking about it.
Okay.
Okay. Let's see here then.
Okay, now I see.
So here I have a function which is g times h. Do you know what f prime of x would be here?
It would be I'm not exactly sure, but I think it's going to be a little bit more complicated, if I recall.
Okay, that's right. So what would be the simple answer? It would be nice and simple if it worked like this, right?
Right.
But sadly, the product of derivatives, the derivative of a product is not the product of the derivatives. You can't just do things in this simple way anymore. Okay, and you don't get to bring notes to the test, right?
Nope.
So we'll have to memorize this rule. So here's the rule. And I'm sure you won't have to prove this. You'll just have to know how to use the rule. So here's the rule. Do you see how you could summarize this? What this says is take the derivative of the first thing times the other function, and also take the derivative of the second thing times the first function, and then add them up. Okay. So we need to memorize that this is the way to, this is what's called the product rule, because product means multiplication. So we can use that, for example, to find this derivative.
Okay.
Now, we can't just use the section 3.1 techniques here, because this is more complicated than the functions we saw in section 3.1. We're going to need to break this down a little bit. So any idea how we could break this down? How would you go about finding f prime of x here?
Okay, so we could rewrite this as 3x squared times e to the x plus e to the x times 3x squared.
Like this?
Yep.
Okay, let me help you with that a bit. Let's actually write this down. It's probably good to write this in more steps. So we could write that like this. So this prime means derivative, right? So this is one way to say that we're taking the derivative. Now,
okay.
I would rewrite it then like this. This is I don't know if your instructor uses this notation, but I think this is good notation for a beginner to use. Do you understand how I got this line?
Right.
So what I'm trying to do is I want to break this down into baby steps so that we don't have to do things in our head. So the point is take the derivative of the first thing times the original plus the original first thing times the derivative of the second thing. It's kind of hard to put it into words, but anyway, now how could I simplify that? What does x3 prime turn into? What does this term become?
3x squared.
And this is still e to the x.
Right.
And what's this become?
X cubed times e to the x.
Notice this is pretty close to what you got before, but unfortunately close isn't good enough in math. So you almost got this when you tried this on your own. The only mistake you made is that you took the derivative of x cubed in both terms. You took the derivative in both terms. Well, the way to avoid those types of mistakes is to break this down into smaller steps. So I would encourage you to use this type of notation that I'm using here until you get the hang of this. Right, that we're trying to take the derivative of the whole thing, and then we can break that down into the derivative of the first times the second plus the first times the derivative of the second. That way we know we're taking the exact right derivatives at each point. So I would encourage you to use this type of notation. Notice that we ended up with a kind of complicated expression. So we're going to end up here with a somewhat complicated expression. So this here would be incorrect. Close, but incorrect. And here's our correct answer. Okay. Does that make sense?
Yep.
All right. Okay, try copying this down, and then you can work it out on your screen. And try to use the notation that we were just discussing, so we have a systematic method here.
Okay.
Good, that's a good notation. Basically, you've just kind of recopied the problem, but that's a good place to start.
So, do that. Okay.
Done?
Yeah.
Okay. Now, it is possible to rewrite that or simplify or factor, but I think that's a good enough answer right there. So that's a good answer. Good. 8x ex. Okay, good. Now, so here's how I would write that out. So you started by writing this. Now, you actually didn't quite use the same notation as I used before. You got the right answer, but on harder problems, you might have some difficulty with that. So let me just show you again what I think would be a better notation. Here's the step that you kind of skipped. This is the step that you skipped. Do you see where this comes from?
You're right.
Yeah.
Right.
And then here's the line that you wrote. You wrote down 8x, because that's the derivative of 4x squared. And you wrote down e to the x here, because that's the derivative of e to the x. So you didn't make any mistakes, but as the problems get more difficult, I think it's important not to skip steps. So here's something else you can add to your notes. I think it's safer to include this step. This shows clearly that we're using the product rule. Also, when you take your exams, the more steps you show, the better, because most people make careless mistakes on exams, and you'll get more partial credit if the instructor can see that your basic method is correct. So you can get more partial credit if you show more steps like this. Okay, but anyway, you did get the correct answer there. All right, there's some other complications that come up on the product rule that are in the practice problems. But since we're running low on time, to finish up, I want to skip ahead and just do one example of the quotient rule so that you have that in your toolkit. So let's say we have this example. So it would be nice here if the derivative was g prime over h prime, right? But it turns out it's much more complicated than that. It's I'm going to leave out the x's here to make it easier to see the formula. Okay. And this is one of the more complicated formulas you'll have to memorize in this class. So here's the formula. You take the derivative of the top minus times the bottom minus the top times the derivative of the bottom. Notice that it's very important to put this in the right order. The 5 minus 4 is not the same thing as 4 minus 5. X minus y is not the same thing as y minus x. So the only way to get this right is if we first take the derivative of the top times the bottom, and then you subtract the top times the derivative of the bottom. Okay?
Okay.
So here's an example. So I'm going to show you on this one what I think would be the best approach.
Okay.
And again, what I'm going to try to show you here is some notation so that we don't skip any steps, because people make fewer mistakes when they're careful not to skip steps. So do you see how I got this?
Yep.
Yeah, that's just rewriting the problem. Okay, and now I should keep the formula up on the screen here. So this is something you'll have to have memorized. So notice we need to do the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So take a look at this and see if you can see where I got each of those terms.
Yep.
Okay, so the point is I'm just trying to show you some notation that your instructor might not have used that allows us to apply this formula without skipping any steps. Okay, and now how would I simplify this? So what does the numerator now become?
The numerator becomes 3x squared times e to the x minus x cubed times e to the x over e to the x squared.
I don't know if your instructor requires you to always simplify things, so we could just leave that perhaps like this. All right, so that's the derivative. You can simplify a little bit, but that's the basic derivative that we have in this case. Okay, good. So anyway, here's the notation that I suggest using. When your instructor does these problems, they might skip this step and go straight to here. But I think it's important for a beginner not to skip this step and to write each of the steps down, because otherwise it's easy to make mistakes. All right. So here's the formula again that has to be memorized. So let me give you this. Oh, no, I already gave you something. Let's see. Back. Where did I put it? Here it was. All right. So back a while ago, we introduced this problem. I think now we have the tools to attack this. So try copying this onto your paper, and then try doing this on your screen. Try to use the same techniques and notation that I was using.
Okay. top. Okay, that's very unsimplified, but I'll leave it right there.
Okay, good. All right, that was a good technique, and that was a good use of the notation that we were just talking about. Now, again, if your instructor did this, they might have kind of skipped the next to last step and just gone straight to taking the derivatives. But I think beginners make fewer mistakes if they write out that step so they can see what they're doing. So that was good. So what does that prime symbol mean?
Prime symbol is derivative.
Yeah, prime means take the derivative. Also, we want to keep this for your notes here. So make sure that your primes don't look like the exponent 1. You might want to put them at more of an angle, kind of.
Okay.
So like you did in your first, you have it kind of at an angle. Some of your primes there look like an exponent of 1. But anyway, you did that correctly. Okay, so to finish up here, now for this same problem, let's figure out f prime of 0. For the same problem, let's do f prime of 0.
Okay.
By the way, I should say one thing you did good there is you put in the parentheses that were necessary. Did we talk about this in our previous session? Sometimes it's difficult in calculus to know when to put in the parentheses. So you put in some parentheses that were necessary in your answer. So that was good.
Okay. So f prime of 0. Okay. I think that's correct.
One moment.
Double check.
Let's see. Okay, are you done?
Yep.
Check that on your calculator.
Okay. So to check this, I can plug in 0 into my derivative formula. Huh.
Let's just check. Let's check that last. But let me ask you this: where did you get the negative 15 from?
Well, in the line above that, I have 2 plus 4, 6. Okay. Alright,
Maybe we don't need the calculator. Just go back and check your work. Where did you get the negative 36 from?
6 times negative 6.
Where did you get the 6 times negative 6 from?
This value right here. 2x plus 4 and 0.
Good.
So 2 times 0, 0, 0. Plus 4 times 6.
You can use your eraser.
Okay. Sorry.
That's okay. Okay. So we were doing great with the calculus, and then we did great with the algebra. We had a little trouble with the arithmetic at the end. That's pretty normal because there's a lot of arithmetic here. So if this was a test question, you just want to be careful to double check yourself. This is a good example of what I meant when I said that beginners make mistakes when they skip steps. It would have been better to show more of your arithmetic steps. Notice that actually we made 2 or 3 different arithmetic mistakes by skipping some steps. So for example, on the top there, well, anyway, so that gave us that. Let's see, 1 second here, actually. So
okay.
2, 0 plus 4 times 6 times 5 times 3 over 36. Okay, how would you interpret your answer?
Okay, so as x increases from 0 to 1, the function increases by approximately -13 over 12.
What does it mean to increase by -13 over 12?
It means to decrease by 1.083.
Yeah, or by 13/12.
Right.
So we can say that if x increases from 0 to 1, the function decreases by approximately 13/12. Okay, good. Okay, so we started today with some of the very simplest derivatives, and now we've gotten to some derivatives that are quite a bit more complicated than the ones that we were seeing earlier. Do you remember how were we doing these problems for the last exam in the previous chapter? Remember that we used that the limit formula?
Limit definition.
Yeah.
Right.
Think about how unpleasant it would be to find the limits of these functions with that, right?
Right.
So remember that for the last test we used the definition of a derivative. F prime of x equals what? The limit as x approaches a, or the limit as h goes to 0 of f of x plus h minus f of h over h.
Right.
You could have figured out every single derivative we did today using that limit formula, but it would have taken you a couple hours for each problem, maybe.
Right.
So the point is, what we're doing now is we're learning shortcuts.
Right.
Now, how would you prove all of the shortcuts we went over? Well, all the shortcuts we went over today could be proven using that limit definition. In fact, your instructor might do some of those proofs in lecture, and they're definitely in the textbook. But as far as your exams and homework are concerned, you don't need to be able to do the proofs. You should know the proofs are based on that limit definition, but all we really need to do is memorize the tricks and then learn how to apply them to special cases.
Okay,
so we've learned now how to do a lot more different types of derivatives here. Okay, so there's certainly a bunch of other applications from section 2 we didn't get to yet. But we went over the 2 main ideas, which are the product rule and the quotient rule. So hopefully, so I think we made some good progress today. I think it's important to go back and try to redo the problems that we just did. Some of them gave us some trouble. You want to get to the point where you can get these right without careless mistakes. And you know, in math, each section builds on the previous sections. So what I was trying to do here is, like I said, there were some parts of sections 3.1 and 3.2 that I skipped over because I wanted to go over the parts that are most likely to be important in the rest of the textbook. So all of these derivatives that we learned how to take today, you're going to have to keep taking these derivatives in the remaining sections of the textbook, and you need to get to the point where these derivatives are easy for you because we're going to keep building on top of it. So it's important to practice these techniques until they're easy for you, because the next parts of the textbook will have harder problems where taking the derivative is just one step. So moving on, let's write, say, f of x equals x cubed times e to the x.
Okay.
And let's find f prime of x.
Well, here, I'll just write this. All right, and I would just leave it like this.
Okay, good. So that's a good use of the notation we talked about previously. I think that's a good way to write out the steps carefully to avoid mistakes, to write out the derivative before we actually evaluate the derivative. Good. So that's a good use of that notation. So let's try writing f of x equals, parenthesis, x squared plus 1, close parenthesis, times e to the x. And
Okay.
let's figure out f prime of 0. Good.
F of 0?
Yes.
Okay.
I'm sorry,
And
f prime of 0.
okay. I was about to say I just wasted my time, I guess. But all right. F of 0. Okay.
Okay, good. That's good. This is one we had trouble with before. So what's e to the 0?
1.
Yeah, before I think we accidentally, we said e to the 0 was 0, but this time we got that correct. What's 8 to the 0?
1.
What's x to the 0?
1.
Yeah, anything to the 0th power is 1, not 0. So we got that correct. Good. All right, so that seems like a good process for this problem. So what you're using here is the product rule. Derivatives don't work as naturally for products as they do for sums and differences, but the product rule is not that complicated, and you got that correct. Okay, so let's continue. Let's try f of x. Let's write down f of x equals x. And let's find f prime of 5. You should write down the question from the beginning so that we don't forget that, f prime of 5.
Okay.
Even though we're not quite ready to calculate that yet.
Okay. F prime of 5. So the derivative of f of x equals x. So function f x is 5. Okay.
Okay. Where did you get the second line that you wrote down? F prime of x equals x. Where did that come from?
We're trying to find x, I guess, and if you take f prime of any variable by itself, it's just itself.
I'm not sure why you said that. Why did you say that?
I thought that was a rule.
Okay. Let's see. Actually, remember that so you're saying that the derivative of the function is the same as the function. But remember, that actually only occurs for functions that are based on e of x, right? The only time the derivative would be the same as the function is when the function was e of x,
Okay.
which is not what we have here.
Okay. So this should be 1, which makes this 1.
Okay, that's right. Okay, all right, so this is something we talked about in a previous session. For some reason, it's usually the simplest problems that give students the most trouble. This is kind of a stripped down simple problem and people lose their intuition here. But your second thought was a good one. Your second thought was to rewrite this in our normal exponent notation. And you saw that x really means x to the 0th power. So your second thought here was a good thought for working this out. So you rewrote this so you could use the power rule. And then that worked out for us. Okay, good. So that was a good approach that you came up with the second time. By the way, you can see this is right, because after all, how would you interpret your answer? How would you interpret the answer you got?
As x increases by 1, the function stays the same.
Try one more time. That interpretation was incorrect. That would be if f prime was 0.
As x increases from 5 to 6, the value of the function is 1.
Okay, that interpretation turns out to be incorrect too, because the derivative doesn't tell you the value of the function. It tells you how much the function changes. So suppose that f prime was 6. That would mean that when x increases by 1 unit, the function increases by 6, right?
As x increases.
Maybe let's back up to a previous example. Back up a bit. Let's see. Yeah, so how about the one that you have here? F prime of 1 is 0.103.
Okay.
How would you interpret that? Or no, let's go back up to an even simpler case. The one where it says f prime of 2 is 0.21. It's on the screen now. Whoops, we passed it. All right, the one where it says f prime of 2 is 0.21 under the cube root of x. How would you interpret that? How would you interpret that f prime of 2 is 0.21?
When x is 2, the slope is 0.21.
The slope of the tangent line. That's the graphical interpretation. Good. And what's the other interpretation we've been practicing?
As x increases from 2 to 3, the value of the function increases by approximately 0.21.
Good. Excellent. That is a correct answer. Good. Notice you wouldn't say that the value of the function is 0.21. Right? You would say the value of the function changes by 0.21. Now let's scroll back down and apply that same exact interpretation to our example here.
Okay. Okay, so the graphical one is when x is 5, the slope of the tangent line to the function is 1.
Good.
And the other definition is that when x increases from 5 to 6, or just 1 unit, the value of the function increases by about 1 unit as well.
Okay, that's right.
So,
I think the thing that was confusing you is that we were using the number 1 in 2 different places in our explanation. But that's not illegal. All right, and you can actually see that's right, because after all, what is f of 5? What is f of 5?
5.
And what is f of 6?
6.
So when x changes from 5 to 6, how much does f change?
By 1 unit.
Yeah, in this case, notice the approximation is exact. In this case, the approximation actually gives us the exact answer. So it really is true that when x increases from 5 to 6, the function increases by 1 unit in this case. In fact, note what is f of 20?
20.
And what is f of 21?
21.
So that's why f prime of any x is 1 in this case, right? Notice that you also wrote down that f prime of x is just 1 in general here, because whenever x increases by 1 unit, the function increases by 1. We can actually check that in this case. This is just a straight line that has a slope of 1. So its tangent line also has a slope of 1. Okay. All right, so I think it's important to keep trying to build those interpretation skills, because they definitely will become more and more important as the class goes on. But let's scroll back down for 1 second just to review that example. So remember at first here, I think you were saying that the derivative was maybe, we had trouble figuring out the derivative of x. So it's important to see that, what our technique here was finding the derivative of x. Okay, all right, sorry. So now you can find some spare screen again, and we'll write down another function. So let's say we'll write down f of x equals and we could write, say, x squared plus 5x plus 2 all over 3x minus 4.
Okay.
Good. And let's try to figure out f prime of 0.
Okay. Let me see. Double check. Okay. This derivative times that minus derivative. Ah. Okay, so I'm going to rewrite this as 5 times -4, 3 times 0, 0, 2 over 16. Well, yeah, 16. Okay. -20 minus 6. Okay.
Okay. Well, you did something on this problem that was of earth-shaking importance, which is that you went back and double-checked your work. That turned out to be a very good decision here. So that's a very important habit to be in, and that's an excellent thing that you did that. So there was one point here where you had made a mistake, but then you went back and you double-checked your steps and found that. So that's good, and that's good that you're doing that during the tutoring as well. We need to keep double-checking our steps during the tutoring because we want to practice the way we're going to play. We need to get into that habit for the test as well. So it's good that you're not relying on me to check the work, but you're checking it yourself. That might not seem like a big thing, but it's amazing how often students just go with the very first thing they wrote down without even checking it. Almost everyone makes mistakes on almost every problem. The good students are the ones that catch their mistakes. So that's good that you're building that habit, especially on a long, complicated problem like this. Okay, so this is the quotient rule. We briefly talked about the quotient rule in our previous session, and it looks like you've done a good job of memorizing that rule. Notice that at first here, when we saw this problem in our previous session, I think your first instinct was to try to factor, to get rid of the fraction. And that's a good idea, but the problem is that most things don't factor. So in this case, there's no particular reason to think this is going to factor, and it doesn't. So instead, we just go straight ahead and use the quotient rule. So that was a good approach.
Cool.
That's the right way to attack that. Okay, so that was a long problem, but you ended up not making any mistakes on that. Okay, so that's a good attack on that. So let's write down another function then. Let's write down f of x equals e to the x over 1 plus x cubed. 1 plus x cubed. Great. And let's find f prime of 1. Good.
Okay. And so this is 1. So we're gonna get 7, 2, I think. Anyway, okay.
Now, one moment, or actually,
I'll just leave it as is, I guess. I'll just leave it like that. Okay. Okay, 1 second. Plus 2 plus 4 1 2 or 4 which equals minus 2.
All right, let's back up for a moment.
Okay.
So on your on your fourth line, you wrote, you have in parentheses 1 plus 3x squared. Point to the 1 plus 3x squared. Tell me how you got that.
3x 3 minus 1 is 2. Oh, this is 0. So this makes this 3. I guess I should apply that rule that we use in organic chemistry where we don't write what feels good, write what makes sense, I guess. But, so this is 3x squared derivative 3x squared 1 2 4. Okay, this should be correct.
Okay, so what would you write down as the answer to the problem? Okay, good. Now, I have a suspicion that you might have been about to write down that the answer was negative e to the x over 4. It kind of sounded like you were stopping there, which is why I asked you that. But when I prompted you, you saw that we weren't done. Because the question, that would have been a good answer if the question was f prime of x. What is f prime of x here? What would be the answer then? Yeah. But here we're supposed to actually plug something in for x. Now, there's something that you did here that was an unnecessary complication. So, for example, how did you get that number 2? E to the x times 2. Where did the 2 come from?
E to the x. Oh, okay. I plugged in 1.
For x.
For x.
But for some reason, you didn't plug in 1 for some of your other x's. Or you waited to plug in for those. I think that the E threw off your intuition a little bit. You waited until the very end before you plugged in 1 for those x's, but some of the other x's you plugged in earlier. Well, we may as well plug them in all at the same time. That just makes things a little bit easier for us. The E just threw off your intuition a bit. So in this problem, since the problem wasn't actually asking us for f prime of x, since it was asking for f prime of 1, we don't need to find that f prime of x is negative e to the x over 4. We can just plug in the 1 one step earlier. Okay, and then we would get to our answer. Okay, so on the problems, the practice questions on the website are all multiple choice, but it looks like the mastery test is not going to be multiple choice, right? It looks like you're actually supposed to write down an answer there.
Right.
So here you actually have to write down the answer. You could now plug that into the calculator and find what this is as a decimal, but I'll bet that your instructor would accept the answer you have here. In fact, maybe this answer is a little better because it's exact. So we can probably just leave this as the answer right here. Okay, good. So that's a good place to start. All right, so this question we got wrong. The one thing that was going wrong is we took one of the derivatives incorrectly. So on the previous problem, I was talking about how good it was that you had double-checked your work and caught the mistake. But on this one, we didn't catch the mistake, so we have to watch out for that. Of course, after you finish the problem, if you have time, it's important to go back and double check each step. But you know what's more important? What's more important is to double check each step as you're going. So let me give you a little speech here. How do most people do problems? Most people figure something out and then write it down. And then they figure out the next thing and they write it down. And then they figure out the next line and they write it down. And then they figure out the next line and they write it down. Now, that might seem like just common sense, but that is a bad method. Here's the right method. The right method is figure something out, write it down, then double check it. Then figure out the next thing, then write it down, then double check it. Then figure out the next thing, then write it down, then double check it. So what I'm saying is the mistake most people make is as soon as they write something down, they try to figure out the next step. But instead, we have to be in the habit, as soon as we write something down, we need to double check it. Because like I said, almost everyone makes mistakes on almost every problem. The key is to catch those mistakes. Since you understand the method here, it would be a shame to lose credit. Okay, so in any case, we have that correct now. It would be good to go back and do this problem again later, since we made a mistake on that, so you can be ready to get the full credit on that. Okay, so let's see. One second. All right, so let's write f of x equals, f of x is 1 over cube root of x. And let's figure out f prime of x.
Okay. Okay.
Okay, good. So we've done that type of problem before, so that's a good way to do that. So let's write down a new function. F of x equals 1 over x to the fourth. And let's figure out f prime of x.
It's the fourth. It's the negative 4. The prime of x. Okay.
Okay, excellent. Great. So we haven't quite done a question like this one before, but I just wanted to point out, just like we can take cube roots out of the denominator, we can take regular old roots out of a denominator too and rewrite them as negative exponents. So that's good. By the way, do you see that there's now another method we could use on this problem? What's the other method we could use here? So the method you used was rewriting it with a negative exponent. What's another way we could figure out this derivative without using negative exponents? There's a different technique we could use here.
Okay, we could use the quotient rule.
Excellent. Okay, that would be a good homework question. It would be a good homework problem to try to apply the quotient rule. How can you tell whether you, when you do the quotient rule, how will you be able to tell if you got the right answer at the end?
If it matches this version?
Yeah, you already know the answer is negative 4 times x to the negative 5, so you'll be able to check your work. Now, your way is better. I'm not saying the quotient rule is the best approach here. The way you did is much better. The quotient rule would be much more complicated. So the way you did it is much the better approach, but it would still be good practice to try the quotient rule as well. But actually, my main point here is that the quotient rule is possible, but it's not the best approach. So the lesson here is don't use the quotient rule unless you have to.
Okay.
Because not because it's wrong, but just it gives you more work than you need. Let's write down another function, f of x.
Okay.
when you're ready, f of x equals x to the fifth divided by x squared. Let's figure out f prime of x here.
Okay, I would go ahead and use quotient rule here, just because I'm not comfortable with exponents in the top. So.
All right, so let me interrupt you. You can use the quotient rule, but can you think of any alternative? What's the alternative approach here?
Well, we could bring this out for sure, just like we did up here, and then this x to the fifth would just be x to the fifth times x to the negative 2, and then now we use product rule.
For the derivatives?
Right.
Yeah, you could do that. What's another approach you could use instead? By the way, you should not have that labeled as f prime, because we haven't taken the derivative yet. We're just rewriting f of x. So what I was actually going for here is, do you know how to simplify the fraction? What is x to the fifth divided by x squared? Do you know how to simplify that? That's an algebra rule.
I have no idea if this is correct or not.
Okay,
but...
all right. How about what you have down below? X to the fifth times x to the negative 2. Do you know how to simplify that? Negative, what do you have written down? Okay, looks like you might have forgotten that algebra rule.
Okay.
So that's a rule that's going to be important in the course, so it's good for us to review that. So when you're multiplying two numbers with the same base, you add the exponents.
Okay.
You don't multiply the exponents, you add them. When you're multiplying two numbers, that's right. And how about when you're dividing two numbers with the same base?
Well,
then you subtract the exponents.
Subtract them.
Notice it would give you the same answer either way. Okay, that's an algebra rule you're definitely going to need in your calculus course, so we may as well review that right now. Notice that what we just went over is not calculus, it's algebra, but it's an algebra rule a lot of people have forgotten. So then how would you find f prime of x?
F prime of x, we could just take...
Yeah, notice how that's a lot easier. If you know the rule, algebra rule, that's a lot easier than using the quotient or product rules. So let's go ahead and do that and find f prime of x. Okay, now if this was a test question, your first instinct would have been best, since you knew that you didn't remember the algebra for this, you really would have been best off using the quotient rule. So that's fine, but as the class goes on, this is algebra that we're going to need anyway, so we may as well review that. Anyway, my point here was that sometimes you can avoid the quotient rule by using algebra and simplifying. On the other hand, if you know that you don't happen to be confident about the algebra, then maybe the quotient rule might be better on that case. Okay, so let's see, where are we now? Okay, so I think you have those basic ideas down from section 3.2 now. So now let's write down f of x equals sine of x. Good. So let's figure out f prime of x. So this we haven't covered before, but maybe you've learned this on your own. Do you know what the answer is here?
Right. So I never took trig, but this one is one of the simpler ones. I think it's negative cosine of x.
That's right. That's right.
Okay.
By the way, what we just did here is not really something you would have covered in high school trigonometry anyway, because what you did was you took a derivative. So that's not based on high school trigonometry. That's not something you missed from high school trigonometry. That's just something new from this course. Okay, so how do you know that the derivative of sine of x is negative cosine of x? Because you just memorized it. We just need to memorize. We just need to memorize those derivatives. We're not going to worry about the groups for this class. Okay, good. So that's one of the derivatives that you just need to have memorized. So let's write down f of x equals cosine of x.
Okay, I need to take that off, right? Yeah.
Oh.
It's just,
Oh yeah. All right. It's a good thing you caught that. Did you look that up? Yeah, you're right. So
yeah,
I guess I don't have it as memorized as I should either. Good.
Okay.
Yeah, so there's no negative sign there. You're absolutely right. All right.
And
so now let's do f of x equals cosine of x. And find f prime of x for that.
anything that starts with a C is negative, I believe. So, yeah. Okay.
Okay, good. All right. So that's another derivative that we just need to have memorized. So let's write down f of x equals tangent x and try to take the derivative of that.
Not going to look. Let's see if I can get it. Secant squared x.
Excellent. Okay, good.
Cool.
That's right. So that's a little different from the ones we saw before. Now let's do f of x equals secant x. And let's do f prime of x.
Sine, cosine, tangent. So this is one of the funky ones. Secant is... I'm just going to look it up. Okay. It seems like some kids in my class, they know these off the top of their head, so I was kind of discouraged at first, but I just need to memorize them.
Yeah, so none of this is stuff that you would have learned in high school, because this is all calculus. So if they know it off the top of their heads, it must be because they just memorized it this semester. It's not something they would have learned in calculus unless they took calculus in high school. Okay, so is this just memorization? Now there are a couple, there's two other trig functions, cosecant and cotangent. Those are less frequently tested. So I just glanced over the mastery test. I don't think I saw any cotangents or cosecants on that mastery test. But if you're worried about that, you can just memorize those on your own. But for the tutoring, we'll focus on these. Okay, so all right, well, we need to memorize these. There's no time like the present, so I'd like you to stare at these until you think you have them memorized, and then scroll them off the screen.
Okay, sine, cosine, cosine, this is a C, negative sine, tangent, secant, squared, secant is just secant, tangent. Okay.
Okay, well, why not just write down all those derivatives? The best way to memorize something is to write it down on paper. So let's write them all out and make sure we have them memorized.
Yeah, that's right. Okay, I just slapped this last one. Okay. Secant. Secant x. Okay, that's right. So it seems like I got this one incorrect, and I worked my way through these top three.
Okay. So again, the key is just to keep practicing that until we have that down. Well, let's scroll to the right a little bit. All right, so let's write down, let's figure out the derivative of cosine x.
Cosine is negative sine.
And let's do the derivative now of the tangent of x.
Tangent is square of x.
And let's do the derivative of secant. Okay, now I noticed that for those last two problems you kind of did a shortcut. Instead of writing the function and then find its derivative, you kind of tried to pack them all into one thing. That notation isn't quite right. If you want to do it that way, I'll go to my screen for a moment and show you how to do this in one step. So here's two ways to write this. So you could write it like this. You could say f of x is tangent x, and now that you've defined the function, you can say f prime is secant squared of x. Or, if you want to take a shortcut, you would do it like this. We've already used this notation before.
Okay.
This is the way to say the derivative of this function is secant squared x by putting the prime over here. So this would be a good way to summarize. So we could summarize the rules we've talked about. So then, what would this be?
Secant x, tangent x.
And what would this be?
That is, it's negative sine x.
And what would this be?
That would be cosine x.
Okay, so this is a good way to summarize those rules using the prime notation we saw before. By the way, something I forgot to mention earlier, I noticed you've been using the prime sometime on your own work. That's good. Be careful when you do that. Don't write it like this, because this looks just like an exponent of 1. We don't want to write it as an exponent of 1. Let's write it off like a little bit at an angle so we can see that it's a prime and not an exponent of 1. Okay, good. All right, so those have to be memorized. Well, let's try this problem now.
Okay, so we're finding the derivative. Okay. Okay.
Let's see. Okay, good. Excellent. So that's a good application of what we've been talking about in the previous sections here. So that's a good use of the notation that we've been using. You used the product rule, and you integrated the product rule together with the new information about the trig functions. That's a good approach. Okay, it looks like we got that right. Okay, good. All right, so let's see. Now let's do... f of x equals x times secant x, x secant x. And let's figure out f prime of pi over 4.
Okay. Okay. So secant. I see sine, cosine, tangent, and then sine to the -1, cosine to the -1, and tangent to the -1.
Okay, yeah. All right, so let me think about what the best way is to do this on your calculator.
And I know
Okay, so actually, the calculator won't give us all the help here. We do need to know a little bit of high school trig for this. Maybe I'll go back to my screen then for a moment.
Okay.
So secant of x is the same as 1 over cosine x. That's the definition of secant. So now if you see this definition, can you understand now why the calculator manufacturers didn't bother putting in a separate secant key on the calculator? Because if you can figure out the cosine, it shouldn't be that hard to figure out the secant, basically. So that's what the secant is going to be. By the way, just in case it comes up, cosecant of x is 1 over sine of x. And cotangent of x, take a guess as to what cotangent of x might be.
1 over tangent of x?
Yeah, this name actually is the one that makes the most sense. The other two are harder to remember. There actually, I didn't see anything about cosecant or cotangent on the mastery test, but just in case, you may as well have these definitions in your notes. But the one that's particularly important to memorize is secant. That definitely comes up a lot in calculus. Okay, so maybe we should do a warm-up then before we go back to the problem we're working on. So let's figure out the secant of pi over 2. So let's put the problem we were just working on hold for a moment, and let's figure out the secant of pi over 2.
Okay, so secant of pi over 2 is equivalent to 1 over cosine pi over 2. So I could just do secant cosine.
Oh, and sorry, I have to mention one other thing here. So so you're using second because it says cosine to the -1?
Mm-hmm.
Yeah. All right. That's a good try, because you're saying that cosine 1 over cosine of x is the same as the cosine of x to the negative 1 power, right? All right, so that's a good try. Unfortunately, the mathematicians have screwed up this area of math by using poor notation. So it's true that x to the negative 1 usually means 1 over x. But here they've redefined it to mean something else. So on the calculator, so cosine to the negative 1x does not mean, it's actually quite confusing. This does not mean cosine of x. It doesn't mean this. Even though, the notation is very bad, even though cosine squared of x, whoops, one sec, malfunction here. Even though cosine square of x does mean cosine of x squared. So one thing to notice is, as a shortcut, exponents can be written in this position. Exponents can be written in this position. However, you can't do that with negative 1. Actually, cosine negative 1x means the arc cosine of x. And what's the arc cosine of x? Or it means the inverse cosine of x. Inverse cosine of x. Now, we haven't reviewed what inverse cosine is. We might have to get back to that later. But anyway, that's a totally different thing than this. So this is all some high school trig that's a little confusing. So let's say we have cosine squared of x. This is an exponent. But let's say you have cosine negative 1 of x. This is not an exponent. It means inverse instead. So the reason I'm saying it's bad notation is that usually this position is an exponent, but not here. So for example, so this means cosine x times cosine x, but this does not mean 1 over cosine x. The mathematicians are just being inconsistent in their notation. So since there's going to be a lot of trig in the calculus course, we have to get used to that. So for example, how would you interpret this? What does it mean?
That is sine of x times sine of x times sine of x.
That's right. So is this an exponent?
Yep.
Yeah, it really is an exponent. Is this an exponent?
Nope.
No. It's just bad notation. Instead, this means inverse sine of x. Maybe I shouldn't call it arc cosine. That's not a good term in a calculus course. We'll just call it inverse cosine. It means inverse cosine okay. So there we go. Okay, so that's all good things to have in your notes. So if you wanted to do an inverse cosine, how would you do that on your calculator?
If you want to do inverse cosine, you would do second cosine.
That's right. So those things above the keys are not negative 1 exponents, they're inverse. Well, we haven't covered that yet. So how can you do this? Well, just don't use any shortcuts, just do 1 divided by cosine x on your calculator. That's the simplest and most straightforward approach.
Oh, okay.
All right, so remember, before that long digression, we were trying to figure out the secant of pi over 2. So let's continue to try that. Oh, I might have messed up on that one. Forget that. Let's try the secant of pi over 3.
1.
Secant of pi over 3.
Sine. Sorry, Steve. Okay. I get 2.
Okay, very good. By the way, what does this number represent here? I know you said you haven't studied trigonometry, but in trig function, the inputs represent angles. So this represents an angle. There's 2 different units for angles. Remember that the input for a trig function is an angle. There's 2 different units for angles, degrees and radians. I don't know if you've had any exposure to radians before. Take a guess, what units do you think pi over 3 is in, degrees or radians?
That's in radians.
Yeah. When angles are expressed in terms of pi, that's usually radians. In any case, so the default in your calculus course is to assume you're working in radians. So I'm just saying make sure your calculator is in radians mode. So I think you got the right answer here, so you must be in radians mode right now. Maybe the whole course you'll be in radians, so maybe we don't need to worry about that. Just if you just leave the calculator where it is, I think maybe you'll be okay. Okay. So we just saw here how to calculate secant. Your calculator doesn't really have a shortcut key for that, so we just do 1 divided by cosine. Okay. So that was our secant. All right, so I think we were in the middle then of a longer problem. What was the problem we were doing? I guess it's on your screen, so we can go back to your screen and now try that.
All right, so f of x was x times secant of x. Rewrote the derivative as such. Okay, so I'm going to plug this in. Secant of x is just going to be 1 over, okay, so 1 divided by cosine secant pi is 4, parentheses, there's this again, plus secant x tangent x. Okay, so I'm going to do that again, parentheses again, 1 divided by cosine oh, I messed up. Okay, pi divided by 4. Okay, plus 1 divided by cosine pi divided by 4, parentheses, times tangent of pi divided by 4. Times pi divided by 4. Alright. I guess I should probably write that out before I plug it in, but hopefully I get this correct. If not, then I should definitely take that approach anyways. One divided by cosine pi of 4 plus 1 divided by cosine pi of 4 times tangent pi divided by 4 times pi divided by 4, and I get 2.525.
Okay, are you done?
Yep.
Okay. All right. It sounds like you were careful with that, and you did get the right answer. We did end up with the right answer here. Okay, good. All right, so so this problem is the first one where we actually had to use some high school trigonometry. The first part of the problem where you took the derivative, that's new material you wouldn't have seen in high school. But then we actually had to do high school trigonometry to actually figure out the actual secants and tangents. And it sounds like you were careful with that, and you did that correctly. So that was a good approach on that problem. Okay, good. And we also saw, yes, how to find secant on your calculator. You have to do 1 over the cosine. All right, so let's find some blank space. And let's try f of x equals e to the x times secant x. And let's find f prime of 0.
Okay. So secant is cosine. Nope. Secant is secant x, tangent x, times e to the x. Okay. And then I'm going to go ahead and rewrite this one more time.
Good. Yeah, that's good.
Okay. So cosine of 0 is 1. Okay. Tangent of 0. So 1 plus. Okay.
Okay, good. That was a good systematic approach. Good. No mistakes. So how would you interpret that answer?
Okay. So the graphical one would be when x is 0, the slope of the tangent line to the function is 1.
Good.
And the other definition is that when x increases by 1 unit, the value of the function increases by 1.
Good. Good. In the past, we got confused when the derivative was 1 because we had to use the word 1 twice in the interpretation, but what you said there was correct. Okay, that's a good approach. That was that took some work, but that came out correct. So let's try another problem. Let's try f of x equals x minus cosine of x. And let's find f prime of 0.
Okay. So we can just, this is derivative of cosine is negative sine. Okay.
Okay, good. So it would have been easy here to make a mistake with the negative signs, but you did that correctly. The negative times the negative comes out positive. All right, good. So how would we interpret that answer?
This answer would be when x is 0, the slope of the tangent line to the function is 1, and also as x increases from 0 to 1, or just by 1, then the value of the function also increases by 1. So we would have a straight line here, right?
Well, no. The tangent is a straight line.
Okay.
How you're saying? Are you saying the function is a straight line? We know it's not, because is the derivative here always the same for any x? We know f of 0 is 1, but does that mean that f of 5 is going to be 1?
Nope.
No, that f of 5 would be 1 plus the sine of 5, right?
Okay.
So the only time that the function is a straight line is if the derivative comes out to be a constant. Okay. That's something you'll probably need to understand at some point later in the course, but to save time, we're not going to. We're focusing mainly just on the mechanics now of calculating the derivatives. Okay, that's good. So let's see. So that came out right now. All right, so let's go on to another problem. Let's try f of x equals tangent of x divided by over x squared. And let's find f prime of x.
Okay. Okay, so derivative of tangent is secant x. I'm just going to double check that. Secant squared, okay. Secant squared of x times x squared minus 2x Okay, so we had derivative of tangent x times the bottom derivative times the top. Derivative of tangent is secant x squared times this value, derivative 2x times tangent x. And then, yep, okay. That's it.
Done?
Yep.
Okay. So what's the name of the rule that you used in your second line?
The second line is that's the quotient rule?
That's right. Good. I think I'll go back to my screen for a moment. So how would you summarize the quotient rule? You can summarize the quotient rule like this. This equals f prime g minus f g prime. Okay, so I'm trying to summarize the quotient rule here. Anything else in the quotient rule?
Yep, we should have it over g squared.
Okay, good. And by the way, this would be a good way to write it in your notes. Oh, so you sent me a handout that summarizes all the derivatives in the class. Are you going to be allowed to use that handout during the test?
I don't believe so.
So that's what you have to have memorized, I guess.
Yeah.
Okay. All right. Any case, I think this is the cleanest, neatest way to write the quotient rule for your notes, however it's written in that handout. So it looks like we left out a part there. So the quotient rule is actually kind of complicated. Okay, so when you're ready, we'll go back to your screen.
Yeah, it's... is it okay if I just... Well, at this point we found nothing. Okay, so I'm going to rewrite all this. And I would just leave this as is.
Okay, good. That's right. So you simplified the bottom into x to the fourth. That's good. You only want to, on the test, you only want to do that simplification if you're sure of the algebra, since your instructor doesn't require you to simplify. So you did that correctly, but if you weren't sure of that simplification, you could just leave it as x squared squared. All right, so we have, let's see, double check this. Sine times x squared minus 2x tangent. Okay, good. Okay, yeah, so at first we had a mistake on this one. So you know the quotient rule, that was just a careless mistake here. So again, it's always important to double check our steps as we're going along to make sure we get the credit that we deserve on the problem. All right, so let's try another question then. Say f of x equals x squared, left parenthesis x squared plus 3x to the fourth, right parenthesis secant x. And let's find the derivative.
Okay. Derivative of secant is double check derivative secant x. Derivative of secant x is secant x, tangent x, and then it stays. Alright, and this is the product rule. And alright.
Okay.
That's that.
Good. All right, that's a good process. So let's try another one. F of x equals x to the fourth over sine of x. And let's find the derivative.
All right. sine of x is cosine of x. This is x to the fourth. Okay.
Good. All right, so that was more practice with the quotient rule. I just wanted to practice that one more time because when we did that previous problem, we'd forgotten to do the denominator of squaring the bottom with the denominator with the squared term, but this time we got that right. Okay, so let's scroll that last problem off the page. Okay, so one more time for practice, try writing down the 4 derivatives, the 4 key trigonometric derivatives. Try to do that from memory without looking at your notes.
Oh, okay. So we could do cosine of x equals sine of x. And secant okay.
Okay, good. Now remember there's 2 more trig functions that we haven't done here. We haven't done the derivative of the cosecant, and we haven't done the derivative of the cotangent because those appear much less often. But I'm looking at the 2 sample mastery tests. There is, so in those 2 sample mastery tests, there's 1 question that does involve cotangent. So it looks like there is a chance there could be 1 or 2 questions on your mastery test that involves cotangent or cosecant. So I'm not going to spend the tutoring time on that, but it looks like it would be a good idea to memorize those derivatives too. So those derivatives are probably on that handout that your instructor gave you. So it would be good to prepare and learn those derivatives as well. Now, yeah, those are the definitions. Those are not the derivatives. So you can go through that and memorize that on your own. But we'll focus on the ones that are the most likely to appear on the exam. All right, so copy that down and then we can try that problem on your screen. Well, I didn't give you the question. So here's the question.
Okay. So 33. 7. Thirty plus 3. That's 27, 35. Oh, that's minus 3. Okay. 8 minus 6. Okay.
Where did you get that 8 from?
That's wrong. Okay, so it's okay.
All right. Now see if you can check that on your calculator.
Okay.
You'll have to be careful entering that in on your calculator. We'll see if we get this right.
Squared. Oh, there.
Yeah, and you can read aloud. Unfortunately, I can't see your calculator, so you can kind of read aloud what you're pressing as you go, so I can follow along and make sure we're hitting the right keys.
Okay, so far I did a left parentheses 5x raised to 2 plus 3x.
Did you go to the derivative function first?
Yep.
Okay, good.
Yeah, so I'm in that function.
Good.
Then I divided that top portion by 2 minus x cubed, and that's closed off as well in parentheses. And now I press comma, and we're taking the derivative in respect to x, so alpha x, comma, and the function at 3. The derivative at 3. Close that off, and I think we'll see. Yep, same answer.
What did you get?
1.0128.
And let's scroll down.
1.013.
Okay, thank goodness. All right, very good. All right, so that's good work. That was a long question there. I'll go back to my screen for a moment.
I was getting kind of sloppy when I was trying to work the problem out, so I just need to focus and make sure I multiply when needed.
Right. Oh, so I kind of cheated there. The best thing would have been if I hadn't pointed out your mistake, and then you could have seen you made the mistake on the calculator, right? Of course, that will only work once we practice with the calculator, so we know we're not making mistakes on the calculator. But anyway, so let's see. So I just wanted to point out one thing to you. Let's say that I want to enter the variable, say, y. Well, I would do that by first hitting the alpha key and then typing y, right? Or let's say, it looks like I have a number stored in there. And let's say I wanted to type the number O, or letter O, it would be alpha and then O. And it looks like I have something stored there, well, 0. If I wanted to do X, I could do alpha and then X here. However, you might not have realized, because the X is used so often, there's a special X key on your calculator up here. And for that one, you don't have to hit alpha. It still works if you hit alpha, but just to go a little easier on you can just hit it directly.
Okay, cool.
So that would just make it a little bit easier to put it in. So if you want to type in any other variable, you always have to hit the alpha key. But if you want to type in X, they've given you a little shortcut here with this key where you can just type it in directly. Okay, so here's another type of problem. You and I haven't worked on this before, but you've probably seen your instructor talking about them or done this in the homework. So give this problem a shot. We haven't done questions quite like this before, but we have all the tools that we need for this. If you get stuck, I'll give you some help, but start by trying it on your own.
Okay. Value h prime. So h of x equals 2 f of x times g. So when x is 0, okay, they give us the values. Okay, I guess. Okay. Trying to find the derivative. When x is 0, f of x is 2. So I guess I should just rewrite the function first. Minus 4 h of x equals 0. Well, h prime of 0 equals. Okay.
Okay, I'm going to go back to my screen now. What's the question asking us for?
We're trying to find the derivative of the function when x is 0.
Derivative of which function?
Of h of x.
Good. Or to just use their symbols, they're asking us for h prime of 0.
Okay.
Okay, good. So we know what h of x is, but you skipped a step in your solution. Before you can plug in 0 into h prime, you need to know what h prime of x is. Do you see how you skipped over that step? We know what h of x is, but we don't know what h prime of x is. So we're not ready yet to find h prime of 0. So let's go through together how to do that. So the first notation I would write down is this. So take a look at this and tell me, do you see where I came up with that?
Yep.
Okay, so the point is, I know I'm trying to find h prime of x, so I've simply written down the function I'm trying to take the derivative of. As we've talked about, it's good not to skip any steps. So what we need to start doing now is simplifying this right-hand side, breaking this down. Can you think of any way to simplify this?
2f of x.
Taking one little step at a time using the derivative rules.
Okay.
I'll kind of show you how to do this. So the first thing we can see is that we're taking the derivative of a difference here. But we know that the derivative of a difference is the difference of the derivatives. So do you see how we went from here to here?
Yep.
Okay. So this is what's called the difference rule. Now, why was this giving you trouble? Because after all, we've been using the difference rule a lot in the past. Well, the thing that's probably giving you trouble is that in the past, when we used these rules, we had actual expressions of x, whereas here we just have the names of functions. So the problem here is that we're just not used to working with functions inside of functions. So we're using the same rules as before, but we have to get used to using them in a slightly different context.
Yeah.
All right. Now, notice this right-hand term. Would you agree that I could just rewrite the right-hand term like this?
Yep.
Yeah. And in fact, if you saw that, you could go straight from here to here. You could just skip over this step. We know that the derivative of g of x can be written like this. Now, how about this term? Do you know any way to simplify this? Well, here we use a rule that you and I haven't talked about very much. We use what's called the constant rule. I think it's called the constant rule. I don't know if it really has a name, but we can do this. That's a rule that we haven't really had to talk about explicitly in the past, but the rule is if you have a constant times a function, you can just pull the constant out of the derivative, so to speak. If you have a constant times a function, you can just pull the constant out of the derivative and just take the derivative of the function itself, if this notation makes any sense. We've really been using this rule all along without explicitly saying so. I don't know if this has a name or not, but this is how to pull a constant out of a derivative. Okay, so that's an important rule for us here. So you can see how I applied that here. We just pulled this 2 out of the derivative. That feels natural. Now, we know in mathematics you can't always do things that seem natural, but fortunately we can do this. This turns out to work. You can just pull this number, this constant, out of the derivative. Okay, so here we are at this line. Does it make sense so far?
Mm-hmm.
All right. Oh, and now we're just about done with then h prime, so we could rewrite this like this. the derivative of f of x could be written like this. In fact, if that was obvious to you, you could skip this bracket step and just go straight to here. I'm just writing down every single tiny little step to make it crystal clear what we're doing. All right, now we've gone as far as we can, and we've simplified h prime of x as much as it can be simplified. We've simplified h prime of x as much as it can be simplified. Well, are we done? Well, what was the question asking us for?
H prime of 0.
So now, only now are we ready to find h prime of 0. So, how would I write that down? What goes in this parenthesis here?
0.
That's right. We're saying 0 is our input. And what goes here?
0.
Good. Notice that there was no way we were ready for this step until we had h prime of x figured out. We have to do things in the correct order. Well, how the heck are we supposed to know what f prime of 0 is?
Well, we don't, but they give us a table, so
right.
I guess.
That's right. So notice how this is different from before. Before we had to figure out the sum stuff. Here they're just telling us. So what should I write down for f prime of 0?
Okay, so when x equals 0, f prime is negative 2.
So I write down negative 2. Good. Notice it would be very easy to be careless and write down 2. But I don't want f. I want f prime. So we have to make sure that we're always reaching for the exact right cell of the table. What did we decide to plug in then? Negative 2.
2 times negative 2.
And now what do we? What's g prime of 0 going to be?
When x is 0, g prime is 1, so we can plug in a 1.
Good.
Okay, this is cool.
Okay, so what's the answer?
Negative 4 minus 1, which is equal to negative 5.
So that's what they were going for. Okay. All right, so that's how to do. This is the type of problem that you and I haven't done before. But maybe now we can see what I meant when I said we have the tools for doing this. We just haven't used them in this context before. So you know all the derivative rules, like the difference rule and the product rule and the quotient rule. You're just not used to using them when the functions are written this way. So we just have to get used to this type of setup. Okay, so let's review what we did here. So notice that one thing that's important here is before you can find h prime of 0, you have to find h prime of x. That was the step that we were skipping in our original attack on this, so we had to do that. And notice that when you're first doing these, it's useful to write down every little baby step, not to skip any steps, like I have here. So here's the original derivative, then we broke that down with the difference rule, then we broke this down with a constant rule. Good. So here we talked about this constant rule for derivatives that you and I have never quite talked about before. Let's make sure we understand that rule.
Okay.
In the past, we've talked about how some letters stand for constants and some letters stand for variables. But I forgot to mention that some letters stand for functions. So you have to always keep in mind, is a letter standing for a constant, a variable, or a function? So that's what we're doing here. So is there how could we simplify this expression?
You can simplify that as r times g prime.
Good. Sorry, this is my cursive k.
Yep.
K
okay.
for constant. All right. So k for constant times g prime. Good. Now I'm going to show you a mistake that a naive student might make, but hopefully we won't. Is this an acceptable use of the constant rule? Can we just take the f out?
Nope.
Well, why not? It looks exactly the same as the previous cases. Why can't we take this letter out when we took the other letters out?
Because we have to know that f and g both stand for functions.
Yeah, so the point is the constant rule only works for constants. It doesn't work for functions, or how about it doesn't work for functions or for variables. So we can take a constant out, but we can't just take any old variable out in that way, if I'm making sense here. So you have to make sure that the number you're taking out of the derivative is a constant, not a function or a variable. So this would be a mistake or wrong. Maybe I'll erase it so we don't have a wrong thing in our notes, but anyway, that's a mistake to watch out for. So the key thing is this must be a constant in order for us to use the constant rule. Okay. So I'll give you another problem. Okay, so this is for the same table that I had given you previously. Let's try this.
Okay.
Try to work this out using the same types of steps and notation that we did for the last problem.
Okay. So the derivative is okay, so it's the best we can simplify. So now we have 1. So when x equals 1, f prime of x is 3. And when x equals 1, g prime of x is 2. Okay.
Okay, good. Excellent. That was a good approach. That was a good notation. So that's how to do that type of problem. I'll go back to my screen. So I noticed that you skipped a couple of the steps that we talked about before, and that's fine. So you skipped kind of over this step, and you kind of leapt right into here, and that's perfectly fine. You just need to know in the back of your head that these are the steps that you're actually going through, and also, if there was a problem that gave you more difficulty, you should respond by writing down more of the steps. Since this problem you were confident about, it was perfectly okay to skip steps. But if there's a problem that you're less confident about, one way to respond to that is write down more of the little steps. So so you should know in the back of your mind that what you were doing steps like this, but skipping over them. Like I say, it's perfectly okay to skip over them. But if the problem gave you more difficulty, then you should write down those steps. Okay. All right, so I'll write something down here on my screen again. Okay, so we'll still keep working with the same table as before, and let's try this.
Okay. Okay. So we have a function times a function. So product will. So derivative of f of x times g of x plus derivative of g of x times f of x. Alright, so the derivative of f of x, well, I guess that's the best I can simplify. So j is 1, or when x is 1, derivative of 3 times g of x 1 derivative 2 f of x 2 4 plus 4. Okay.
Okay, one moment. Okay, check your next to last, well, yeah, check, you made a mistake in the very last line.
Oh, wow. Three plus 4.
Okay, so if this was a test problem, it would always be good to double check even simple arithmetic on the calculator, because most people are pretty poor at simple arithmetic. All right, so we ended up the right answer. Okay, good. This problem is harder than the previous ones, but you adapted and worked out how to deal with it. The extra level, so notice that it's a little more complicated to apply the product rule than it is the difference rule, but you adapted and you did that correctly. Notice that this was the first time that we needed stuff from the table, not just for f prime and g prime. This time we also needed stuff from the table for f and g as well. We hadn't seen that in the previous examples, but you adapted to that and plugged them in the right place. So we just have to be very careful here not to confuse f with f prime or g with g prime. But I think you did a good job of doing that. Okay, it looks like you worked out how to do that. So I'll go back to my screen. Good.
Okay.
Let's try this one.
Okay. Okay. All right. So, derivative of the function. Roll. Oh. So that's the simplest form. So when x is 0, well, e to the 0 is just 1. So 1 times the function is 2 plus derivative -2. Okay, 1 times 2, 2 plus -2. Okay.
Okay, one moment. Okay, that's good. All right, that's a good
Cool.
application again. This problem was a little bit different than the ones before because in the previous problems we were just working with the names of functions, f and g. But here we have a kind of a mix and a match. On the one hand we have a function that only has a name, f, but then on the other hand we have an actual function, e to the x. But that didn't seem to mess you up. You still applied the same rules as before, even though one function only had a name. So that was a good way to adapt to that problem. Okay, good. Let's see, so I'll go back to my screen here. So you had to figure out, for this problem, you had to figure out this. You had to work out this derivative. Now, is e a variable or a constant?
E is a constant.
So why couldn't you just use the constant rule and say this?
True.
So would this be allowed? Could we just use the constant rule and say this? Can we just take the e to the x out using the constant rule and just take the derivative of f? Would that be allowed?
We can't because there's a variable.
Okay, yeah. All right. For a second there, I think I'd kind of tricked you into the wrong path. But yeah, so does the constant rule apply here?
It does not.
But e is a constant. Well, it doesn't matter because e to the x is not a constant. So I was trying to trick you into going down the wrong path, just because I see people make that mistake sometimes. Okay, so we can't apply the constant rule here because even though e is a constant, e to the x is not. So this would be wrong. You can't apply the constant rule here. Instead, you have to apply the product rule. So what you did was absolutely correct. What you did was absolutely correct. And what I just showed was just a common mistake we want to make sure we watch out for. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you.